Do you love math? If you do love math, I suggest to go to www.mrmathinc.net or YouTube Mr. Ing today. Very easy and compatible to work with.
Hey math lovers, let's go over Integrated Math 3's Lesson 1.3, Complex Numbers. What's our learning targets? Our standards for mathematical content. Know that there is a complex number, so we're going to be focusing on this one, I, such that I squared equals -1, and every complex number has the form of a plus bi, with a and b are real numbers. NCN2 tells us use the relation I squared equals 1, and then commutative, associative, and distributive properties to add, subtract, multiply complex numbers. How can you meet the standard? I can perform arithmetic operations using imaginary numbers. What are the math operations? Well, you can go all over here in green. Communicative, associative, distributive, but more importantly, we know these: add, subtract, and multiply. All right, let's go ahead and try this warm-up. Go ahead and try it, and then when you're ready, you can do it with me and press play. All right, in our warm-up, we need to simplify the expression. Well, you'll notice that you have, I'm going to circle it here, you have addition here. So you don't really need the parentheses, and all you can do is just combine like terms. Notice that these have no x's. So 2 plus 5 gives me 7. And over here, these are like terms because they both have a x in it. You could put a 1 in front, so -3 plus 1 is -2x is our answer. Notice how I was saying the expression above is equal to this, and then I box my answer. Let's try question number 2. Same thing here. Now this one, this negative sign here, you're going to have to do something with it. And so what you can also think of it as a -1. We're going to distribute a -1. Let me show you what that can look like. So I'm just going to rewrite this. I don't need the parentheses now. 7 minus 3x, -1 times 6, and -1 times 4x. And we can just go through and simplify. 7 minus 3x, that becomes -6 and minus 4x. Then I'll just combine like terms right here. -3 and -4. So -3 minus 4 gives me -7x. And 7 minus 6 gives me a 1. You can put the 1 right there. And box your answer. Let's go on to question number 3 now. We're going to have to do the same thing on this one. I'm going to have to distribute that -1. So -1, -1. -1 plus 5x, -1 times the -2, and -1 times -8x. So this becomes -1 plus 5x. Remember, this is multiplication here, so that becomes +2. Same thing here. Negative times negative is a positive, so positive 8x. And these are my like terms, so I get 5 and a positive 8. It gives me 13x. And over here, -1 plus 2 gives me 1. 1 plus 13x is my answer. I can't add those two because they're not like terms. It's like adding a blue and a green. You can't say the answer is 14 blues. You can't say 1 plus 13 greens equals 14 greens. No, they're not like terms. Okay, this one, you should notice that they are next to each other, so this is multiplication. You could use something called FOIL, but I'll tell you why I don't like it, because it only works with this particular case. And essentially what I do is I do the same thing, but I just use this box. And what I'm going to do is write 2 minus 3x, and over here I'm going to write 5 plus x. We're going to do the same exact thing you would use for FOIL. We're going to multiply and then we're going to add or combine like terms. Okay, let's go ahead and do that. 2 times 5 is 10. 2 times x is 2x. Negative 3x times 5 is negative 15x. And negative 3 times x is negative 3x squared. I just multiplied here, so let's go ahead and combine like terms now. So I'm going to do this one. You could do shapes if you want. There's no other one that's combined with that one. So I have negative 3x squared. Okay, here in the boxes here, these are like terms. So negative 15. So I'm just looking at the numbers in front. That's called the coefficient. So negative 15 plus 2 is negative 13x. And then you're just left with a positive 10. So there's my answer. I'm going to double check that. That's correct. And the last one. Okay, the common mistake is to think you could distribute this, and the answer is that's incorrect. That would work if it was something like this. Should put an X, maybe I'll put a Y. Well, let's say you had something like this. What's the difference between these two problems? This one is a negative and this one's a multiplication. So this only works for the laws of exponents. So that's not the situation we have here. This one is telling me that I have 2 sets of these, right? So I have negative 2 minus 8x and negative 2 minus 8x. Basically, I'm going to do the same thing we did above, multiply and then combine like terms. So let's go ahead and draw a box here. It's so cool now. I learned if you just hold down my pencil, it makes these straight edges. And so negative 2 minus 8x, negative 2 minus 8x. Okay. If you don't do this, what happens is a lot of students try to multiply the yellows and then the last one, the greens. And that's wrong because you're missing some middle terms there. So negative 2 times negative 2 is positive 4. Negative 2 times negative 8x is 16x. Negative 8x times negative 2 is 16x. And negative 8x times negative 8x is 64, pay attention, x squared. Because remember, x squared is really just x times x. All right, let's go ahead and combine like terms. So this one by itself. And these are like terms. So when you're combining, it's really adding. So 16 plus 16 gives me 32. X. Again, I don't write the square there because you're just adding the numbers in front. And then the last one is by itself. You just have a plus 4 here. And there you have our warm-up. Let's go ahead and move towards the...
Electrical engineers use algebra to describe voltage, current, and impedance, or resistance to current. In alternating current systems like those you use every day, different parts of the circuit are active at different times. However, the other parts of the circuit still carry certain voltages, current, and impedance, even when they are not active. This cannot be measured by a real number, but can be measured with a complex number, which contains both real and the imaginary part.
All right, you just watched the launch there. And the answers are algebra, circuit, not active, real, and then complex. Okay, let's go over here to some vocabulary words. And in our vocabulary words, the principal square root of -1. This is called the imaginary unit. Should not write with a highlighter. Imaginary unit called I. What does I stand for? An imaginary unit. And later you're going to learn the principal square root just means the square root and then of -1. I equals the square root of -1. Okay, moving on to our next part. A number of the form bi, where I is a real number and I is an imaginary unit, that one should say b. This is called a pure imaginary number. You'll have something like this, a plus bi, and the part that makes it pure is that you just don't have a real. Okay. A number that can be written in the form of a plus bi, where a and b are real numbers and I is the imaginary unit, this is called a complex number. Complex number. Okay, the next part is called the word complex conjugates. And we'll use this when we're dividing them, but the two complex numbers of the form, and all you really have to do here for conjugates is just change the math operation. If it's plus, you're going to change it to minus. Those are conjugates. Or if this was a minus, you would change it to a what? Plus. And a method used to eliminate radicals from the denominator of a fraction or fractions from a radicand, they call this rationalize the denominator. Okay? So you might be asking, what are pure imaginary numbers? What are pure imaginary numbers? Well, remember we did something like this. X squared minus 1. Let's just say you graphed that. And look at my colors up here. The C value, remember that's, x squared plus 0x minus 1, and then you have standard form, and then, A is 1, B is 0, and C is negative 1. Well, the C of negative 1 here is your y-intercept, and my graph's going to look something like this. And the big idea here is that it goes through the x-axis. We talked about how going through the x-axis, this means those are real solutions. But what would happen if the graph did something like this? We said that it doesn't touch this blue line here. So we would say no real solutions. And today we're going to learn what are they talking about this. Okay? So the big idea for all of 1.3 is this. They kind of do an italicized I, it doesn't really matter, equals the square root, I'm having fun coloring here, of negative 1. And I have a silly phrase, you're going to laugh and just say, Mr. Ng, you're so silly. I say, what do pirates say? You might think, arr, but pirates really say, I. I is the square root of negative 1. That's what pirates say. So that is our big idea. So what is a pure imaginary? We talked before that you have a plus bi, and in some ways this is the real part, and over here is the imaginary. Okay? So if I basically just cross off the real part, then you have something like this, and this is called a what? Pure imaginary. It just doesn't have a number in front. It doesn't have like 3 plus 2i. So here's a bunch of examples of pure imaginaries. You might have something like 6i. You might also have something like negative 2i. You might have something like I radical 3. Notice you don't have this part in red, 0 plus something. You don't have 1 plus 6i. If it's just 6i and it has a 0 in front, you just zeros you don't need to write. So that's called a pure imaginary. Same thing. If that 0 was gone, negative 2i. If it was a 3 minus 2i, that would not be a pure imaginary number. Okay? So let's go ahead and do this concept check here. Okay, quick lesson on exponents. You know, shouldn't say I. X to the third power is the same thing as x squared times x to the first. X to the third power equals x squared times x to the first. Why? Because when you have the same base, you can do what? You can add the exponents. 2 plus 1, and that's how you get the 3. Okay, so if we already told you, you kind of saw it is if I do something like this. The big idea, let's just write it here, let's just copy this, because we can do something like magic. This is my big idea here. Oh, I didn't want to do that. Duplicate, that's what I wanted. Okay. Now I messed it all up. Okay, so we just said that I equals the square root of -1. And really that just has something to the first power, right? So if I do something like this, what is I squared? Well, I squared is the same thing as I times I. And if I is equal to the square root of -1, I can do a substitution there. I can write square root of -1 times the square root of -1. And if you think about it, the square root of -1 times square root of -1, they're both in the same house. There's 2 of them. And then the index is the same, then you're just left with its principal root, which is -1. So this answer right here is I squared equals -1. Okay? Now let's see if we can keep using this pattern to fill out the rest. I to the third, I to the fourth, I to the fifth, I to the sixth, I to the seventh, I to the 8th. See if you can see a pattern. You try it. What are each of those equal to? And then I'll do it with you. Okay, so I to the third is I to the third equals, you can do a couple things. You can do something like I squared times I to the first. Does that make sense, right? We just said, you know, same base, multiply the same base, you add the exponents. So if my base is I to the third, that is I squared times I to the first, or I squared plus 1. But that's going in a circle. So I squared, look at the green box that we just had over here, this green box, and I squared equals -1. And then the yellow box over here is the square root of -1, or you can just call it I. And so I want to say that I to the third is equal to -1 times I. You don't have to write -1. You can just write -I. Okay, let's see if we can get I to the fourth. Now you could choose I to the third times I to the first, but I think just I to the fourth equals I squared times I squared. And that was our green box over here, this thing. So it's basically equal to -1. -1. All I'm doing there is just some substitutions. I'm trying to prove something, a pattern you can see, and it is a problem later on. So I to the fourth equals what? +1. So I to the fourth equals +1. See if this gives you hints to get the rest of them. All right, I to the 5th, you could do I to the 4th. I think that's the easiest one, actually using I to the 4th, because it's red, and if it's red, then it's -1. Watch. So I to the 5th is equal to the I to the 4th times I to the 1st. In the red box over there, we said that I to the 4th is equal to -1. And this one you just fall down, so you just have that one. I think I messed up my pattern, but it's okay. And so I to the 5th is equal to, you don't have to write the 1 there, so that just becomes -I. -I. All right, let's do I to the 6. I to the 6. What color have we not used? This light blue? Let's try this light blue. I to the 6 is I to the 4th plus I to the, times I to the 2nd. Remember, you could have done like I to the 3rd and I to the 3rd, but 4 is a great one to use. Why? Because, what is I to the 4th? We said it was equal to -1. And then we said I squared is equal to what? Also -1. So using the 4th and the 2nd one are best. And therefore, I to the 6 is equal to -1 times -1, which is what? +1. All right, last two. What would I do for the last two? I would use, how about 4 and 3? So I to the 4th is equal to -1. So we're just doing a bunch of substitutions here. Okay, I to the 3rd is equal to -I, right above us. And so then if you simplify that, you'll get negative times a negative is positive, so just one I, or just what? I. I, matey. And the last one, ran out of colors, just use dark purple. So I to the 8th is I to the 4th times I to the 4th. I to the 4th is -1, -1, multiply those, and hopefully you're seeing a pattern here. This will equal +1. And you can do this pattern all day long, but it helps you kind of just derive them. Okay, so that is our concept checked. Let's go on now to page 2. All right, let's go over this 1.31 square roots of negative numbers. What's the big idea? We've talked about this. What did pirates say? Pirates say I is equal to the square root of -1. And as we do these problems, I'll just give you a couple of steps that might be really helpful. Factor the radicand. You might be asking, what is the radicand? It is the stuff inside the radical. Number 2, factor out the imaginary unit. And number 3, simplify your life. All right, let's do this one. So we need to get everything in the inside, and let's go ahead and factor that. So you could do something called the factoring tree, but it also tells us first to factor out the imaginary unit, which is -1. Okay, so I'm thinking of some numbers. You know, you could try something like 2, 3. 3 works. Let's see. 3 goes into 20. Goes in 7 times 21. Maybe 8, 9, 9. That's what I wanted to write. 27. So That gives you 24, and 3 goes in 24, 98. So 3 times 98. What's half of 98? 45, 47 would work. So you have -1, 3, and then this is 47. What did I say? 47, 49 times 2. And then the 49 is really 7 times 7. So there's my... Can you guys see the factoring tree there? I call these prime factorizations. -1 times 3 times 2. Okay, what can come out here? What can come out? Well, you have a pair of them, right? I told you about the story about the scary neighborhood. If there's 2 of them, they can come outside the house. But when they're outside the house, you're kind of scared, so they're really close together. So the answer would be, coming out would be a 7. And what is the big idea here? What's the square root of -1? I. And then you just have what's left over inside the radical. So 3 times 2 would be 6. And this is actually how we write our answer. It is 7i radical 6. Okay, so directions below. Go ahead for questions 1 to 6. Go ahead and do 3 problems and skip 3. And then go ahead and press play if you want to see me do each of those problems, or just check your answer. All right, question number 1. I'm just going to factor out the imaginary unit, so that would be -1, -1 times 48. And what you're trying to do here is actually look for the ones that are called perfect squares. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, right? So 1, 4, 9, 16, and 25. This one's a little bit difficult, but 16 times 3 is the best one. But now, if you don't see that, most students are probably going to see 6 times 8. So let me show you guys 6 times 8. And then 6 can be broken down to 2 and 3. And 8 can be broken down into 4 and 2. And you don't really need to go down all the way down. Okay, so you have a pair of 2's, so those come out. The square root of 4 is really 2 times 2. And then what do pirates say? Pirates say, I. I is square root of -1. So that's square root of -1 equals I. Okay? And then I just look what's inside there. I didn't circle, which is the 3. And then you can just simplify that. That would be 4i radical 3 is your answer. All right, let's take a look at question number 2 here. Square root of -63. I'm going to break that into our imaginary unit, so -1 times 63. Then I'm thinking 63, the factors of 63 are 9 and 7. So I have -1 times 9 times 7. So square root of -1 is I. Square root of 9 is 3. And then you're left with the radical 7. So the square root of -63 is equal to 3i radical 7. Where did we go? All right, let's try question number 3 here. Let's break it down into our prime factorization. So that would be -1 times 72. 72 is 9 times 8. Oh, there's a better one. Can you think of the better one? Watch, when I break it down, you'll recognize what the better one was. Okay, let's say you broke it down into the total prime factorization, all the way down. This would be 3 times 3. This one would be 4 times 2. And then you would do something like that is 2 times 2 times 2, right? And this is how you double check your answer. You actually multiply all of those. So 2, that's 4. 4 times 2 is 8. 8 times 3 is 24. 24 times 3 is 72. 72 times -1 is -72. Okay, so I wanted to show you why 9 times 8 was not the best one. If you actually multiply all of those, 9 times 4 is 36. I should have done that. 36 times 2. Why? Because that one is just going to be 6 squared, or 6 times 6. Does that make sense? Okay, so watch. We have a 3 out here. You got a 2 out here. And what do pirates say? Aye. And the 2's left in there. So that would be 6i radical 2. Remember, if you check your answer here, just want to show you guys that the 6 goes back in. There's 2 of them. So it's not 6 times 2. That would be 36 times 2, which is 72. And if the I goes back in, well, that's just negative 1. So that would be negative 72. Okay? Question number 24. Let's factor out negative 1 times, what do you guys think? 12 times 2, that would work. You can list them all out if you want to. 4 times 3, 8 times 3, I can't multiply. 4 times 6. I like the 4 times 6. Because this one becomes 2, right? That would be 2 times 2. Yeah, pair. And the pirate here, that's the I. And you're left with the radical 6. Oh, circled it for me. Let's look at negative 84. Factors, 84 times 1, 42 times 2. How about 3? Does 3 go in there? 260, no, can I not count? 6, 2, 2, 4, yeah, 8. Let's see if there's a 4 goes in there. Oh, that's even better. 21. I like that. 5. No. 6. 6 goes in there. Goes in once. 24. Goes in 14. 7. Goes in 7, right? Once. And then 12. No, not hopeful. 8. No. 9. No. Okay, so which one's the best one? I like that one. So let's go ahead and do that. So square root of negative 1 times 21 times 4. The square root of 4 is 2. Square root of negative 1 is I. And what's left is 21. Double check our answers over here. Yup. Alright, 99. So square root of negative 1. How about 9 times 11? This is I. Notice how this is on the outside there. Square root of 9 is 3. Remember, guys, if that doesn't make sense, just break it up into, when in doubt, write it out. It says Professor Berger is his name. When in doubt, write it out. So you see how it's a pair and then it comes out? That's why I wrote 3 here. Okay, and the 11 is not circled, so that would stay on the inside, and this would be our answer. Again, you might ask, where did the negative go? Because we know that pirates say I equals the square root of negative 1. Okay, we're going to do the same thing we did above, and we're just going to factor out the radicand, or what's inside the radical, and then factor out the imaginary unit, which is I. Find those pirates. So, square root of 10, square root of negative 1, square root of negative 1, and square root of 150. This one becomes I on the outside. Here's another I on the outside, and we have radical 10. And look at this, you can put them in the same house. Should be 15 there. And that is times 15. Okay, so what can we do here? How about, let's just, I get I squared is 150. I think of quarters. let's do 25. Because the square root of 25 is what? 5. So this is going to give me, okay, now we have to go back here. Way back into time. I squared equals -1. So write that on your formula sheet. Formula sheet's just a way for you to, I squared equals -1. We keep using that information. So if I apply that to this problem right here, this is now -1. And the math operation is multiplication there. So this would become -5 radical 6 is my answer. Okay, question number 7. Negative radical 23. So let's just go ahead and take out the imaginary part. And same thing here, -1 and 46. So that becomes I, that becomes an I, and then I have radical 23. This one is going to be radical 23 times 2. So now I have I squared. What? Big white. I squared. The 23s are a pair, so they can come out. So that is 23i radical 2. 23i squared equal times radical 2. And then we just stated from over here that I squared is equal to what number? -1. So 23 times -1 times, whoa, that turned mine into an arrow, but it's a radical sign. So -23 radical 2 is my answer. And question number 8. Same thing, let's separate them. -1 radical 6. -1 radical 3. You guys see the big idea here? Square root of -1 equals I. That's what we're learning here. And these are both underneath the radical, so you could do 6 times 3 is 18, or you can just stop there and just do 2 and 3. And then this is the green 3. And then you'll see the pairs. So this is a pair. I circled the wrong. This is a pair. They come out. It's only one number. So we have 3 I squared radical 2. What is wrong with this? Well, we had said over here that I squared equals -1. I squared equals -1. Do you see this? All of that is going to turn into what number? -1. So those become -3 radical 2. And our last one. -1 times radical 5. This one is -1 times 10. So this will become I, and square root of 50. That does not look like a 50, Mr. Ring. 50, and so this will become I squared 25 times 2. The square root of 25 is 5. I squared is equal to what number? From above, from our chart, that equals -1. And you're left with a 2 there, so I have -5 radical 2 is my answer. Okay, let's go ahead and try number 10 here. You're going to do the same thing here. I'm going to multiply all the constants. So 3 times -2 is -6. That'll be -30. Okay, pay attention. I'm only going to do this one here. And the reason why I chose that is because we learned above that I squared equals -1. Like, where'd the pirate go, Mr. Ing? It is I equals I the square root of -1. So if I do this idea, I have -30 times -1 times I. And then you can just simplify that to be positive 30I. We like to write the I are kind of like the variables on the second part there. Okay, number 11. We have I to the 11th power. And so from our chart, or from I squared, you could do something like this. Let's break it up. So I squared to the 5th power. Okay, look at this, look at this. Does that make sense? Because if you add 2 plus 2 is 4, 6, 8, 10, 11. Does that make sense? That gives me the 11. Okay, so you can use your properties of exponents. I to the second, how many of those green ones do I have? 1, 2, 3, 4, 5. And if we just said I squared equals -1, then I can say all that is equal to what? -1. Okay, -1 to the 5th power, you put in your calculator, is essentially just -1. So I have -1 times I, so we just call that -I is your answer. All right, what do we got? Number 12. I'm going to split this part up. Well, not split it up. It tells me I have 2 of them. 2 sets of parentheses. Let's go ahead and multiply the constants. 4 times -6 times -6. So -6 times -6 is positive 36. 36 times 4 is 4 extra 2, 144. Okay, let's do I times I is I squared. And I still have this blue I there. Okay. And what do we learn about I squared? I squared equals -1. I squared equals -1. And we just multiply all that. And you're going to get -144I. And that's it. Let's move on to lesson 1.33. All right, 1.33 equations with pure imaginary numbers. Do this one with me, x squared plus 81, and they're asking us to solve. Solve means x equals something. We can put in a number, square it, add it to 81, and get 0. Okay, so if you use your algebra skills, you already recognize that it's already isolated. And I also want you to notice something else if you put it into standard form. This is the A value. There is no B value, and this is a C value. Does that make sense? And so, and let me just write this, x squared plus 81. So when you have just A and C, this sets you up for a method called the square root method. Square root method. solving quadratics by the square root method back in, I believe, 1.1. Because we said there was solving quadratics, we've been focused on graphing, and now we've been focusing on a different method when you have only A and C. So the first thing you're going to do is we're going to isolate x squared. And to do that, solving, I'm going to give you my little trick, is you go PEMDAS backwards. Let me say that again. If you're simplifying, you do this way, simplify, S phi. But if you're solving, you go backwards. You go addition and subtraction first. So down the equal sign. Whoops. I'm going to subtract 81 from both sides. You're going to be left with x squared equals negative 81. Right? I don't need to write this. I don't need to write that 0. Okay. Now, so from doing this, we just did addition and subtraction. If there was like multiplication or division, that would be like if you had like a 4 in front, you would do multiplication, division first, the red number first. So we don't have anything there. Next, we're going to do parentheses and exponent. So to get rid of the exponent, you have to take the square root of both sides. Okay. So isolate x squared. And then what are we doing? Take the square root. Take square root. Okay, what happens here is this is a pair and it can come out, so you're just left with x. Pay attention. You must write this one in plus or minus. Okay? I'll explain that in a second. And then do what we've normally done. You have negative 1 and 81. Square root of 81 is 9 times 9, so that comes out. And you got a lot going on here. And then, of course, where's the pirate? It is I. Okay, so let's see if we can clean this up a little bit. X equals plus or minus 9i is our answer. Okay, what does the plus or minus mean? It basically means it's two solutions, positive 9i and negative 9i. That's what it means. And you go back to the original problem right here in black. Something squared equals negative 81. And we said that there were two solutions, so I'm showing you why this works. 9i and negative, let's use blue, negative 9i. If you follow along, 9i times 9i, you'll get 81 I squared, and I squared equals negative 1. So 81 times negative 1 gives me what? Negative 81. And then you can do the same thing over here. Negative 9i times negative 9i. You have positive 81 I squared, and then I squared is equal to negative 1. And that's why it's a solution. It makes it true. That's what solving equations does. Okay? All right. For directions for questions 13 and 18, skip 3 of these, and then basically doing the same thing we did. Solve the equation. Okay. Number 13, if you choose to do this one with me, I like to draw down the equal sign. We said we're going to isolate, so we're going to subtract 45 here. You're left with 5x squared equals negative 45. Remember, if you guys need to, always write, I'm just going to write it down here, PEMDAS backwards. So this is to simplify. Neat little trick. And then over here, you're going to go solve. So we're doing solving. Does that make sense? So do this part this way. So I just did subtraction, addition. Now I'm going to do multiplication, division. The common mistake here is trying to take the square root, and that doesn't work because how do you take the square root of 5? You cannot find two identical numbers. So we're going to first divide by 5. This will give me x squared equals -9. And now we can take the square root of both sides. This will give me x equals square root of -1 and square root of 9. The square root of -1 is where my pirate is. That is I. Okay, pay attention here. We should have a plus or minus right here. You have to have two answers. And then the square root of 9 is 3. The answer is x equals plus or minus 3i. Again, you add the plus and minus in there because there are two solutions. Because if I put in 3i back in there and I just say the positive one, that works, but there's also one missing, that is -3i as a solution. Let's try number 14. Same thing. Let's go ahead and isolate. Look back, should we divide or take square root? We're going to divide here. So you're left with x squared equals -6. Let's take the square root of both sides. This undoes one another in some ways. I'll show it to you, kind of cancels. You're just left with x. Okay, here it is, plus or minus. And this breaks up to -1 and square root of 6. And this one becomes I. Okay, now this one is a little bit, looks weird. So you have x equals plus or minus I radical 6. And that is our answer. Let's try number 15. You realize it's already isolated, so all you have to do in this problem is just divide by -9, and you're going to get x squared equals -1. Take the square root. Remember, there's a 2 here, that cancels, right? Does that make sense? What's happening? You're left with x equals plus or minus, and then this is I. And that's our answer. Remember, if that doesn't make sense, you could take x and put it back into the original equation here. Take like -I squared, you get I squared equals -1. -1 times -9 gives you a +9. All right, number 16, we're going to do the same thing. All right, we're going to isolate (7x squared) equals -84. We'll divide by 7. We do that to isolate x squared equals -12. And we're going to take the square root of both sides. I do that because that is an invisible 2. And what that does is it cancels the exponent and it's called the index and the radical sign. So you're just left with x equals, don't forget the plus or minus, and you split this one up. So I have square root of -1 and the square root of 12. All right, we got to do a little bit more work on this problem. So this is 4 and 3. Don't forget their square root. Remember, there is your I. So we have plus or minus I. And the square root of 4 is 2. That's coming outside the radical. So you have x equals plus or minus 2I radical 3. Notice how that 3 is still inside. And then we're going to box our answer right there. And that's our answer. Double check, that was number 16. Let's go ahead and try number 17. Okay, so let's go ahead and subtract 125. Get negative 125. Divide to isolate x squared. Negative 25. Take the square root. Remember, there's a 2 there. You need two identical numbers. Boom, gone. You're left with x equals, that is negative 1 and square root of 25, which is 5 times 5, right? And you have a pair, so those can come out. That comes out as 5. Don't forget your plus or minus. So I always say when you are solving radical equations like we're doing right now, make sure to do plus or minus. Make sure to do, that's a sure, to do plus minus. Okay, so what are we left with? This one is I. There's nothing left in the radical sign. And that's our answer. X equals plus or minus 5i. Number 18, subtract 96. Eight x squared equals negative 96. I'm going to divide by 8. So you're left with x squared equals negative 12. Okay, square root. Remember, now we have the plus or minus. You have to add the plus or minus because it has the two solutions, negative 1 and 12. And that one becomes what? 4 and 3. This one you can take out. Square root of negative 1 is I. And square root of 4 is 2. So we get 2i. X equals plus or minus 2i radical 3. It would be okay if you said x equals plus or minus I2. But you would not say something like x2. We say 2x. We say the number, then the variable. So that's your answer for number 18. Let's go on to 1.34. All right, let's go over 1.34, equate complex numbers. And before we do that, let's talk about complex numbers themselves. What is this wonderful math family? I'm going to draw a chart. Okay, in this family there are what we call complex numbers. And that is in the form of a plus bi. Now, when b real numbers, when b is equal to 0, there are kind of like two regions. So I have this green region, and we'll call this gray region. And then, all right, so we have something called, I'll call it Q. It's just a letter, but rational numbers. Something like 1/2. Okay, within rational numbers, or on this other side, the gray area, then you have something called I for irrational numbers. Like pi. Pi is irrational because it just keeps going on forever. All right, within rational numbers, you have a family called Z, which is integers. And within integers, you have something called W for whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then within this, you have something called the N, which is natural numbers, which include 0. Okay, on the other side, if b is not equal to 0, and you have something called imaginary numbers, and in here you just have a family. Let's use a different color. Then you have something what we talked about was called pure imaginary numbers, when a is equal to 0. Okay, so that's just a little bit about complex numbers. Okay, let's look over here and do this example with me. Find the value of x and y that makes each equation true. So this is the equation they're going to give us. 5x minus 7 plus y plus 4i equals 13 plus 11i. Okay, so I'm going to highlight this. Hopefully you can see this. The part that has no I in it is this part over here in green. Okay, so that is equal to this part. Okay, so we're going to write an equation, 5x minus 7 equals 13. And the part that is the imaginary parts is here in blue. Well, how do I know that? It's right in front of the I, because I stands for imaginary. And that is equal to this one here in blue. So I have y plus 4 equals 11. And all you have to do here is just solve. So remember, use PEMDAS backwards. Let's write that. PEMDAS. You're going to simplify, and then you go up to solve. So that's why I'm doing adding and subtracting first. So 5x equals 20, and then you just do division and multiplication. So if I divide by 5, x equals 4. Okay, over here, do the same thing, just subtract 4. And we're going to get y equals 7. And for you to check your answer, which you don't have to, but just trying to help you understand, if I put a 4 here, and for y I put in 7, you'll get 20 minus 7, and this one becomes 7 plus 4i, and then you got oh, I did a bad thing right there. It should have been here in parentheses. So that'll become 7 plus 4, which becomes 11i. And over here, 20 minus 7 gives you 13. So I'm just trying to show you like why you're solving for x and why you can put it back into that equation and it makes it true. Okay, so down here, questions 19 and 24, skip 3 and same directions. Find the values of x and y that make each statement true. Go ahead and press play if you'd like to see me do it step by step. All right, let's go ahead and highlight the parts that are the same. So in this problem, this one has no I. And this one has no I in it. So I can do 9 equals 3x. So we get x equals 3. And when you do this part now, pay attention. I'm not doing, I know it's the imaginary part, but I'm taking its coefficient, what goes in front. You see that? If I divide by 4, we're going to get y equals 3. Okay, let's try number 20. So here I have x plus 1. And this is the part that doesn't have I. And if you need to, you can always start with the part that does have I. And this is a -6. So that'd be 2y equals -6. There's multiplication. The opposite is division. That equals 1. So y is equal to -3. Okay, looking over here. I have x plus y equals 3. And we subtract 1, and we're going to get x equals 2. Let's try 21. Again, you can start with the I if that helps you. So 3 minus y equals 6. And let's just solve that one. So what would I do? I would probably just subtract 3. Negative y equals 3. Remember, that's like an invisible -1, so I would divide -1 on both sides. Y equals -3. Okay, this whole portion over here has no I, and that equals to the real part. So that would be 2x plus 7 equals -4. And again, use your PEMDAS. I'm going to use addition and subtraction first. I'm not going to divide here. So I would subtract 7. It's going to be 2x equals -11. Divided by 2, and you're going to get x equals -11 halves. That negative sign goes with the fraction line, and it's up and down. All right, question number 22, same thing. Let's highlight the imaginary part first. So that goes in front of the I. In front of the I. And then you just get to solve a linear equation here. So add 7. I get 3x equals 4. Divide by 3, I get x equals 4/3. Over here in blue, it's the part, all of it has no I in it. So 5 plus y equals 9. I'm using the opposite, so this is positive 5, so I'm going to subtract 5. And I get y equals 4. Let's try question number 23. You can focus on the part here. This one has no I, no I. So if I divide by 5, I get x equals 4. If I do everything in front of the I, I'll get negative 12 equals 4y. And divided by 4, we'll get negative 3 equals y. Okay, so again, put the one in front of I. So negative 16 equals negative 2y. There is multiplication there, so opposite is division, so divided by negative 2. I'm going to get y equals 8. Okay, so over here, I just have x equals 3. And that would be my answer. Alright, 1.35, add or subtract complex numbers. Basically what this is just combine like terms. Just like we did in that warm-up. So let's go ahead and try this example here. I have a parentheses 8 plus 3i. You'll notice that it goes real and then the complex. So nothing with I and then something with I. And this time we're going to subtract that from 4 minus 10i. Okay, just like one of that warm-up problems here, this negative sign you can think of it as two ways. They call it the inverse, which means you change all the math operations inside, or you can distribute a negative 1. So if I distribute this negative 1 here, I'm going to go ahead and drop the parentheses over here. So that would be negative 1 times 4 and negative 1 times negative 10i. This would give us 8 plus 3i. That becomes a negative 4 and positive 10i. And then you have the reals here. You're not doing something crazy like opposites. It's just adding. 8 plus negative 4, 8 minus 4 gives you 4. And this one over here will give you, these are like terms because they both have I in it. And you're just looking at the coefficient. So pretend it's like 3x and 10x. That would just be 13x. So we call this 13i. So you notice my answer will have the real first and then the complex. For questions 25 to 30, go ahead and skip 3. Your directions are to simplify these. And go ahead and press play when you want to see me do it step by step, or you just want to check your answers. Okay, for number 25, I recognize that it's a plus, which means I don't need to distribute or anything. You can drop the parentheses. So I'm going to have 6 plus I plus 4 minus 5i. And I can just combine like terms here. So 6 plus 4 is 10. And remember, this one doesn't have anything, so you can put a 1 here. So it's really just 1 minus 5, which is negative 4i. And that's your answer. For number 26, this one has a negative sign. So you can make that a negative 1, and you can go ahead and distribute that negative 1. So that'll give me, I don't need the parentheses on this left side, 8 plus 3i. And then negative 1 times 6 and negative 1 times a negative 2i. This will get me 8 plus 3i minus 6 plus 2i. And then I'm going to go ahead and just combine like terms. That becomes 2. And this becomes plus 5i. Number 27, Again, this one has a negative sign, so you can think of it as a -1. So -1. Don't need the parentheses here because there's nothing unto the outside or to the left of the parentheses. So 5 minus I, -1 times 3, and -1 times -2I. Let's clean this up. You're going to get 5 minus I minus 3 plus 2I. And we're just going to combine like terms here. So that would give me a 2. Put a 1 here. So that's -1 plus 2 will give me a positive 1I, or just I, right? Because there's a 1 in front. Number 28. This one's going to be nice and easy because this is a plus sign. So you don't need all these parentheses. And you can just combine like terms. Super easy. That'll give you 2. And then remember the numbers in front of I. So 2 minus 3 is -1I, or -I. Remember, that's just like 2 minus x. There's always a 1 in front. Does that make sense? Hopefully that helped. Okay, number 29. This one's nice and easy. That's a plus sign, so I don't need to distribute anything, and I can just I don't need the parentheses. So I have the reals. 6 plus 4 is 10. And then -3 and then -2 gives me -5I. Would it be wrong if you wrote something like this? -5I plus 10? It would not. Again, they just like the real and then the imaginary part. Number 30. Uh-oh. I see that negative sign. Let's go ahead and distribute that -1. So -1 times a 1 and -1 times a -5I, right? Pass out candy, everybody's got to have it. Can't just give it to one kid, they won't be happy. Okay, so I got -11 plus 4I, that becomes -1, and then positive 5I. Okay, that becomes -12. And 4 plus 5 gives you 9. 9I is our answer. All right. Let's move on to 1.36, multiplying complex numbers. Do this example with me. Complex numbers are often used with electricity. In these problems, J is used in place of I. They'll tell us why. If not, maybe I'll help you. In electricity, the voltage V of an AC circuit, you know that plug in the wall, 3 holes you put in your outlets and stuff, can be found using the formula V equals CL, where C is the current and L is, or I is the impedance. Impedance? I don't know. If C is equal to 3 plus 2I amps and I, or I think it's L, because they want to be stuck with imaginary numbers, L equals 7 minus 5J ohms. Determine the voltage. Okay, so the first thing I'm going to do is just use that formula. V equals C, and I like to write a cursive L. Why? It's not cursed. I just don't want it to look like a 1. Okay? Okay, so let's just color code this. C, whoa. C is going to equal 3 plus 2J. Okay? And L is going to equal 7 minus 5j. Okay, so this will, it says determine the voltage. That's just what is V, right? Okay, so then it tells me another piece that I need is this one. J is usually used in place of I. So I'm not going to use the I anymore. The J. What am I going to write? We're going to write an I. That's it. V equals, well, we have to do some math, but we kind of navigated the word problem portion. Okay, so what do? We get to do the box method. And I just basically get to write 3 plus 2i and 7 minus 5i. This is just like the warm-up. You can use FOIL, but I'm just going to use this area model or the box method, and we're going to do the same thing. We're going to multiply, and then we're going to add or combine like terms. Okay? All right. 3 times 7 is 21, and 3 times negative 5i is negative 15i. 7 times 2i is 14i. Okay, pay attention to this one. 2i times negative 5i is negative 10i squared. Okay, we got to remember one of our big ideas. One of the big ideas is I equals the square root of negative 1, or I squared equals negative 1. So if I know that I squared equals negative 1, every time I see I squared, I can write negative 1. And this will give me negative 10 times negative 1, which is positive 1. And then now, we just need to combine like terms. So, this is a real number, and this is a real number. 21 plus 1 gives me 22. And then 14i and negative 15i, that's just 14 minus 15 gives me negative 1i, or just negative I. And if the I business, again, let's go back to the up here, it says use J for I. So let's go back. We can say that V equals this, V equals this. So V equals 22 minus J. Okay? So big idea here is use the formula, use a box method, and then simplify. All right, directions for questions 31 to 34. Skip one problem and go ahead and simplify. Okay, let's go ahead and use this big idea here. And I'll just do some magic. Oop. Oop. Okay, so 31. Let's go ahead and multiply first. Okay, 2 times 3 is 6. 2 times negative I is negative 2i. 3 times I is 3i. And positive times a negative is negative. And I times I is I squared, right? Same base, you add the exponents. And yeah. Okay, let's use that big idea over here. I squared is equal to what number? Negative 1. And don't forget you already had that negative on the outside, so that just becomes positive 1. So let's go ahead and combine like terms. I have 6 plus 1, which gives me 7. I have 3i minus 2i. Those are like terms, so I just look at the numbers in front. That just becomes 1i, or just plus I. $32, let's do the same thing. Let's go ahead and draw a box. I recognize if you hold it down, it'll make your line straight, kind of, most of the time. Alright, so 5 minus 2i. And it doesn't matter how you write this. You could have wrote 5 minus 2i on the top. Does not matter with this area model. Okay, 4 times 5 gives me 20. 5 times negative I is negative 5i. Remember, pretend it's like an x, so it would become it would be negative 5x. 4 times negative 2i is negative 8i. And negative times negative is positive, and 2i times I is going to become 2i squared. Alright, remember what we just learned, that I squared from up here, I squared equals negative 1. So instead of writing I squared, what am I going to write? Negative 1. And remember that's a multiplication, so that becomes negative 2. So that'll become 20 minus 2, which is 18. And negative 8i minus 5i gives me negative 13i. Now pay attention, that's not negative 13i squared, because you're just adding, which means you just go the numbers in front. Okay, so that was number 32. We completed number 31. All right. 33, same thing. Four minus 2i and 1 minus 2i. So 4 times 1 is 4. 4 times negative 2i is negative 8i. Negative 2i times 1 is negative 2i. And negative 2i times negative 2i is going to be positive 4i squared. Okay? Why is that the case? Because if you just write them next to each other, that just becomes negative or positive 4, and that is, remember, multiplying the same base or same variable, you add those numbers, so that becomes 1 plus 1 is 2. Okay, here it is. Remember this big idea here? That becomes negative 1. So that is negative 4. So 4 and a negative 4 gives me 0. And negative 2i minus 8i is going to be negative 10i. And you don't have to write the 0 there, so we just write negative 10i is our answer. All right, use the formula V equals CL. Let's write that down. Find the voltage in the circuit with the current. So C equals that. And the L impedance is this. We're just going to multiply it. You can convert these to I's or J's, or just keep it as is, and then I like to put the I's in there. And why do I like to do that? Because that's what we've been learning. Because what do pirates say? I. Alright, so let me just write this other one on the side. And 3 times 3 is 9. 3 times negative I is negative 3i. 2i times 3 gives me 6i. And Negative I times 2i is negative 2i squared. And what do we have up here in our big idea? I squared equals negative 1. So negative 2 times negative 1 gives me positive 2. So I have 9 plus 2, which is 11. And 6, now we're adding, right? 6i minus 3i gives me 6 minus 3, which is just plus 3i. And that is our answer for number 34. All right, last one, 1.37, divide complex numbers. You can go ahead and press pause if you want to go ahead and copy the chart I made, blue, green, and yellow. Okay, so basically this represents real, complex, and this is the number of zeros. So if I graph this, x squared minus 1, it has a y-intercept of negative 1, and this is a parabola. That's not negative 1. Let's try that again. Y-intercept of negative 1. This is my parabola. Okay, and remember that the real here is how many times it touches the x-axis. And in this case, how many does it have? We have 2. Okay, pay attention. The number of zeros is, let's use a different color. This 2 here tells you how many times it's going to cross, or how many quote-unquote solutions we have. So that would be 2. So what number can we write there? 2 plus something equals 2. Well, if you think about it, all of these are going to be quadratic, so there's going to be 2 zeros. Okay, so that means that number has to be 0. There are 0 complex, and I'll show you visually what that means. Okay? All right, so let's go ahead and graph this one again. Let's graph x squared. Okay? This is called the power function. It just doesn't have a y-intercept. If you had to write a number, it would be plus 0. So there's 0. And there's my graph. Okay, question. How many times is it crossing the x-axis? Okay, it's kind of a trick question, but we talked about this. I know you see that it touches the graph once, but we call that one a double root. It counts as double, right? Why? Because the answer is x equals 0 and x equals 0. Okay, so we have 2 reals. That means how many complex do we have? 0. Okay, let's do the last one. This last graph here has a y-intercept of plus, that's a 1, sorry. And your graph's going to look like this. Okay, question. How many times does it cross the x-axis? Whoops, that's supposed to go over that. The answer in this case is 0. Okay, what does this mean? That means what number do I have to write in there? This one would be 2. Okay? So it's the same thing, real, complex, real, and then the number of zeros. Just copy and paste it. Should have done that. Okay, this is the number of zeros. Number of zeros. Okay, what do you guys notice? Is it possible for this to have is it possible to have just like 1 real plus 1 complex? The answer is no. So here's the big idea. that's a star. Complex conjugates come in pairs. How many is a pair? There's 2. And here I'm going to drive it home right here. Okay, what is the conjugate? Well, if this is a plus, that means this one's going to be a minus. That's it. You just change the math operation. So if it tells you a minus bi, then the conjugate is a plus bi. If they give you a plus, you change it to a minus. Okay? That's it. So let's go ahead and try these really quickly, and then we're going to do a more advanced problem. Okay, this one is plus, so this one's going to be what? Minus. Simple as that, guys. This one is minus, you're going to change it to a what? Plus. This one is a plus, you change it to a minus. This one is a minus, you change it to a plus. Okay, this one looks tricky, but if you notice what I've done there, I have the real and I have the complex. So you can put a 0 there. That one is a minus, so you'll change it to a plus. And everything else is the same. So these are the conjugate pairs. See, it's exactly the same. The only thing that's changed is what? The math operation. Okay? All right, let's do a more complex problem. Let's do this one. It says simplify 5i over 3 plus 2i. Okay, so if you look back at our vocab, we're going to have to do something called RTD. And RTD is basically we can't have I there. We rationalize the denominator. So to do that, we just need to find its conjugate. So let's just make this super obvious. What is the conjugate? What did we just do there? Well, if this is a plus, then this one has to be a minus. Yeah. And then everything is the same. Okay, now pay attention. So now, when you're doing rationalize the denominator, you're going to have to always multiply a number times 1, right? 4 times 1, 4. Pi times 1, pi. Sine of 3 pi over 2, you don't know what that is, but it's the same. Sine of 3 pi over 2, you could evaluate and get a number, but my point is, if you multiply any number times 1, it doesn't change. So that's the same thing here in math here. Okay, what does this mean? Okay, this means we need to multiply this numerator here and this denominator. Okay? To multiply the denominator, if you recognize what we have to do in this work here, is we're going to have to use the box method. So let's go ahead and multiply the blue there. Do it over here. So I have 3 plus 2i, 3 minus 2i. What you're going to see is the i's disappear. That is the whole point. Multiply 9, negative 6i, 6i, and negative 4i squared. Okay, here's a nice thing. Negative 6 and positive 6 equals 0. It goes away. We learned that pirates say I equals square root of negative 1, which helps us figure out that I squared equals negative 1. So everything in blue, if you think about this, this will just become 9, and a positive 4, which would give us 13. In the green, we're going to have to distribute this 5i. So that'll become 15i minus 15i squared. And of course, we just did it. I squared equals -1. So that is 15, -15 times -1. This will give us 15i plus, that becomes plus, yeah? Plus 15 over 13. Let's see what we did here. Yep. Pfft. Why did I write? Did you see that? Okay, that becomes 15i and then -10i squared. Okay, so that is -10 times -1. That will give me positive 10. Okay, now if you wanted to separate this, you can do a couple of things. 15i plus 13 and 10 plus 10 over 13, because they have a common denominator, you can combine them, right? And why am I doing this? So that I do the real first and then the complex. So that would become no I and then the one that has an I. Make sense? And that's our answer. So to simplify that problem, you're going to look at the denominator, look at its conjugate, and then go ahead and multiply. All right. For questions 35 to 37, go ahead and skip one of these. Let's go and tackle this one right here. I'm going to have to multiply by its conjugate. Remember, if this is a plus, then this one's going to be a minus, and I have to do it both top and bottom. So let's go ahead and get this one in green. Three plus I and 3 minus I. So we're going to multiply, then add 9, -3i, positive 3i, and -i squared. Positive 3i and -3i equals 0, and I squared equals -1. So that'll become 1. So 9 plus 1 in green, this will give me in the denominator a 10. Okay, here I'm going to distribute 5 times 3 is 15, and 5 times -i gives me -5i. All right, they both have a denominator of 10. And in this problem, you can simplify. So 5 times 3, 5 times 2, 5 times 1 times I, and I'll show you why I did that, and then 5 times 2. And you'll see that 5 divided by 5 is 1. Same thing over here. So you're left with 3 halves minus I, or 1/2. You could do 1/2 I is fine, or you could do I over 2. And that's our answer. Let's take a look at number 36. Okay. 36, you're going to need a math operation in front. What is that? That's going to be a 0 plus I. Now, what is its conjugate? Pay attention. I don't really want to do 0 minus 2i. You could, but the conjugate there is just going to be a minus, and then it's just 2i. You'll recognize if you do the 0 in front and you can go ahead and use the box method, you'll get the same answer. So let's do the denominator. What did I just tell you? You didn't have to. Let me show you. I'll just do it super fast. Let's just say you want to put a 0. You don't have to. But it's the same answer. Multiply 0. 0 times anything 0. 0 times anything 0. And then negative 4i squared. That becomes a negative 1. Negative 4 times negative 1 is 4. So the answer is 4 for the denominator. And that would make sense because if, let's just say I don't have it, let's just move this down. Magic. So 2i times negative 2i gives you negative 4i squared. Does that make sense? And it's the same math as I did over here. So that's what I'm trying to tell you. You don't need the 0. Does that make sense? But I did it over here on the left side with the blue is because I wanted to show you how to find the conjugate. Okay, this one looks a little bit weird, but you can distribute backwards. Okay, so 7 times negative 2i is negative 14i, and that'll become plus 26i squared. And we know that this is negative 1, so 26 times negative 1 gives me negative 26. Negative 26 divided by 4. And if you want to simplify that, we can break them up, the fractions first. Negative 14 over 4i minus 26 over 4. Did you notice they both have a denominator of 4 there? And let's just break them up to prime factors. So this will become negative 7 times 2 over 2 times 2i minus 2 times 13 over 2 times 2. And let's go ahead and just cancel some things out here. And I get negative, I'm going to put it second over here because that's the complex part. And the one without the I is the real part. Okay. And then same thing over here for number 37. To help you find its conjugate, I'm just going to put a 0 here. And that's just to show you the conjugate is just going to be minus. And the best one is just to write 3i. That's it. The conjugate of positive 3i is negative 3i. And then all you have to do for this problem is multiply across. And this one you're going to have to distribute. So that's going to give us 6 times negative 3i is negative 18i. Negative 5 times negative 3 is positive 15, and that becomes I squared. 3i times negative 3i becomes negative 9i squared. Big idea is that becomes negative 1. That becomes negative 1. So negative 18 plus 15 times negative 1, and negative 9 times negative 1. So this will give us I made a mistake. Did you see that? I caught it. Okay, so negative 18i minus 15 over positive 9. And then I'll just break them up into factors. Or sorry, we'll split the fraction. So negative 18 over 9i and negative 15 over 9. Real, then complex. And you're like, what math operation goes in between them? It's going to be a negative. Does that make sense? Or whatever the whole expression is equal to. So This is 5 times 3, 3 times 3. This is a negative because negative divided by positive is negative. 9 times 2 and 9 times 1, I. So 3's will cancel and your 9's will cancel. You're left with negative 5/3 minus 2I. Alright, let's double check our answers just to make sure. 3 halves minus 1/2 I, minus 13/2 minus 7/2 I, negative 5/3 minus 2I. That's it, guys. And those you can skip, okay? So that's complex numbers. Plus you.
Shout out to Mr. Ang for being the best math teacher that there is. And math is easy.